in regards to our 5-step simulation process, we want to explain how we come from a CAD geometry, which by the way could be a wireframe geometry or a solid geometry, up to final simulation where we can validate and simulate the geometrical quality and see which contributor is the most important for the quality requirement. However, starting with the geometry, we can make a drawing-based process, which means then we have to translate everything from the drawing, like assembly sequence, like measurement plans, or even tolerances, by hand into the system to come to a final simulation. What we're going to show to you today is all is integrated in the CAD, and we can or how 3DCS fit to the 3D master strategy. So that means everything, as I said, is in the geometry, and we just import that from the geometry into our simulation to come to the final validation simulation part. So let's start with the CATIA integrated version, and as you can see, we brought a lot of 3D tolerances to a single part, and the single part now will be handed over to a assembly. And inside the assembly, we use the constraints to make the system understand how those two parts will be assembled to each other. Okay, this is where the most CAD designers do stop on in the assembly design, and now let's go one step further, where we change the workbench from assembly design into analyze simulation, and here we are talking about the 3DCS analysis. Okay, then we should run an update to get the simulation tree. However, you can see also that we have some scenes, which is a normal CATIA functionality, for the simulation purpose, I moved the part in a kind of exploded situation. Is that really needed to make 3DCS work proper? Clearly no, it's just very helpful for the user to understand what has happened. Okay, the first thing I like to hand over is how the part's getting assembled. Because if I using that button here and hit nominal build to make them assemble, then you see nothing happens, because we do need the information in the simulation how the part's getting assembled, and this is containing the constraints containing those information. So just taking this workbench and then let's import the constraints and joints into the simulation. And this is what I did here, and you see the tree get enriched. Now if I hit nominal build, you see the part are moving properly together. And this is also why we have that explosion situation, because of seeing the part working step by step together. Okay. The next thing I like to integrate it is the 3D tolerances into the simulation. So therefore I hit the next button and I say, okay, come on, let's import those 3D tolerance information. And of course, out of those 3D tolerance information, you can also hand it over to a drawing, and this is an internal loop. When we update tolerances here and you open the drawing and hit update, they will be also updated as well. However, now we also have integrated the tolerances into our system, as you can see here. And now let's bring them together and we can start to make them shake. And this shaking, what you can see is in regards to the Monte Carlo simulation, which is the base for our geometrical validation. So that means the single parts will be, or the geometry of the single parts will be changed randomly by the tolerances. We do find randomly a situation, assemble as described here, visualize it, and run all measurements, throw it away, do it again and again and again. This is like in the real world. First, you produce the single parts, then you pick the single parts out of the single parts boxes randomly to a assembly. If you measure that assembly, you find a certain value. If you do the next assembly, you never will measure the same because of single part tolerances, because of geometry effects, because of assembly line effects. And this exactly is the shaking, what you can see here, where you can see all the influences from all those contributors. And here you can see how the assembly is running up. And no, there is no factor behind. It's a one-by-one factor. However, when we're done, then we can hit a simulation, and we get, for all measurements we did integrated in our system, the result. And not only the result, but also the contributor in a priority list, which single influence have which influence to the final result on the quality measurement. This is our entry window, where you can sort in regards. Come on, let me show the critical one on the top, to make me understand which one I have to focus on at the early time. If I did that, I make a double click to move a little bit more inside to make me understand a little bit more in regards to where is the biggest issue I do have. And here in that window, we find several statistical value, as well as I said, the contributor in a priority list. What it does is also make me understand with show max. Let me move that a little bit more inside that we can see a little bit better. So with show min and show max, we see it move. And this show min, show max move the situation to the borders of our result. And as I said, pictures saying more than 1,000 words. However, we can do the same in each contributor, where we say, okay, why is that contributor is on the top? What is that contributor doing with my result also for that one? And we can then say continues, and we see how this tolerance make the part a move, and this is why it is inside the result. And here the goal is also that we are running one simulation and we get all those measurements in one shot, where we also can move from measurement to measurement and make us understand what if we do have an issue, and if yes, what is the issue. The next point is how to get this result into a reporting process. And here's how the process normally or usually work. And at the moment with our simulation, we are in the upper right corner, and we call them digital test lab. And out of the digital test lab, if you just think about what this is all contains, so all measurement points, all directions, all important stuff for doing a physical measurement and getting reported is within the digital test lab. So the next step we want to look is how we do hand over this one to our template maker. And this template maker is in regards of how a result should look like, and how or this template will be filled up with physical measurements on one hand, but also with digital measurements out of our digital test lab. However, let's have a look to that path, and therefore we are switching over to our template maker. And now let's see how easy it is to come to results. So we just take that part inside the template maker. We can extend a little bit the window. We can rotate and make them look good. Now, as we do have the CAD editors inside our template maker, we also could import the data from um, the part, and then we can go and define a chart table. So we do have several of them, and let's take a export in R or a run chart. Let me see if I can find a run chart. Yeah, just stay with that and say okay. And then what we also can do is going here and sort data. Maybe we want to sort them by the nominal, that all charts which belonging to the same nominal is at one page, for example. And then as we can do also, we can have a auto sort our stuff. However, with that, we can start to make our template looks nice, and then finally we will come to our finally template where we program everything together, and also using different types of charts to report the result. Until now, we are here and hand it over to the QDM gateway as one hand to fill it up with physical measurement or with digital measurement. Also, what we can do is in regards to the FDNA, we can hand over to our colleagues from Metrology